Okay, good afternoon, everyone. Good afternoon. Good afternoon. A couple of things before I start today's lecture. First things first, can everybody hear me? People in the back, right? And this goes without saying. If you cannot hear me or you cannot see my writing clearly, please give me a shout out. Okay? All right. First things first. Homework. Good news. It is on Carmen. Okay? So this is available under Carmen quizzes. After today's lecture, you should be able to solve this homework without much sweat. But this is not going to be the story for the future homeworks, because we will be building on top of the material from the previous week. So typically, homework assignments will involve material predominantly from the previous week's instruction. It is very rarely that I will solve something in class today and ask you to submit it on homework tonight. Okay, that's very, very rare. In that instance, it is just going to be something that's a piece of cake, and all I want to see is if you're a warm body in class. All right, that's the predominant reason for that. All right, that's one thing. On Carmen calendar, I have listed all your assignments. Okay, this is a common complaint that I get that, okay, hey, I don't know when my assignment date is. Now you know. No balking, okay? All right. So that's that. Then the last news before we go to lecture is today I'll start my office hours at 4:30, just for today, okay, because I have another engagement that I have to fulfill as a part of a faculty member. But from next week, we will resume regular service. Fridays, 10:30 to 11:30, I'm all yours. Friday, 4 to 6, I'm your constant silent companion. As long as you have any questions, please feel free to speak up during my office hours. They'll be held on Carmen Zoom. They are not in person. They're on Carmen Zoom. So please don't come to my office. I won't be there. You're welcome to see my office from the outside. All right. Any questions, please, before I proceed? All of you able to access my notes on Carmen? So this is an unwritten rule. After class, give or take a few hours, I will upload the lecture video for the class, and I will upload handwritten lecture notes. Those lecture notes may go a little more detailed on what we are covering in class. I may have a few more examples as well. Okay, so please take a look at those notes. If you're having any issues with the homework, consult your class notes first, consult my lecture notes next, consult your brain next, then talk to me. Okay? All right. So let's begin. By defining what is meant by a linear system, because linear systems are what we're going to live and breathe for the rest of this semester in 3260. Okay? Linear systems, they are characterized by two main features. Okay? Of course, this is a characteristic of any typical system as well, but predominantly linear systems. So characterized by a physical model and by a mathematical model system model. Okay? The physical model of a linear system is the representation of the linear system using linear connected elements. The physical model in the form of linear elements. Of course, this begs the question as to what is meant by a linear element, which is precisely what I'm going to define next. A linear element bears a linear relationship between its input and output. Okay, so linear element, linear relation between BET dot between input and output. So when I say linear systems, what's a system? We looked at it in the first lecture. It's a collection of elements. Is it a random collection of elements? Do I have no other work in life? No. It's a collection of elements that is designed to achieve a desired purpose. And in linear systems, as opposed to non-linear systems, which are scarier beasts, I use linear elements, and we're going to talk about it exhaustively as the time proceeds here. They're characterized by a linear relationship between input and output. Okay? From the physical model, by applying governing equations, or apply physics laws, we will obtain the mathematical model of the system. And for all linear systems, no matter who tells you what, for all linear systems, the mathematical model is always a linear ordinary differential equation. Okay? So the mathematical model is a linear ODE. Last class I defined an ODE, ordinary differential equation. Okay? This is true for all linear systems. And of course, we are going to define what is meant by a linear ODE. Okay? That is my next order of business anyways. And before I proceed with that, let me see if I have space. Probably not. The following are the types of systems that we will study in system dynamics. Okay? Mechanical systems, we will study electrical systems, we will study fluid systems. I like to call them as hydraulic systems, okay, and pneumatic systems. So fluid systems. And lastly, thermal systems. Each system will be characterized by its foundational physics laws. Mechanical systems, Newton's law. Electrical systems, I have conservation of charge, I have conservation of energy, okay, applying Kirchhoff's current and voltage laws. Fluid systems, conservation of mass, conservation of momentum and energy. Thermal systems, same story, different variable, temperature. If I look at mechanical systems, what's my aim? My aim is to characterize the relationship between the input, which is the force applied on a system, and the output of the system, which could be the displacement of the mass of the system. If I look at electrical systems, what's my order of business? I take voltage as a source, send it into the system. Perhaps my aim is to measure the voltage across a set of different terminals in the system. Fluid systems, we've seen this last class. Volumetric flow rate could be the input variable. The fluid height present within the tank could be the output variable. Thermal systems, thermal energy into the system from a heat source. What's the output of the system? The temperature of the system. And so we're going to see this for each and every system. We're going to see them as disjointed entities. That is, you'll first study mechanical systems, then we'll study electrical systems, then fluid systems, and then thermal systems. In 3360, which is the next course in the sequence, what you're going to do is, you're going to start combining the systems together. Okay, take the mechanical and electrical system, make it into a braking system. Take the electrical and the thermal systems, make it into a refrigerator unit. Something of that sort, which is much more complicated only on the level of modeling. The fundamental concepts are all the same that you see here. Okay, I want to stress this multiple times. Alright, so that's our main business here. Modeling of all these systems, physical models, mathematical models, use governing rules, obtain the mathematical equation, and then solve the damn thing using Laplace transforms, using frequency response analysis. Unpack the meaning of that system and proceed further in life. Sounds good? Very interesting, very, very interesting. And complicated, but don't be bogged down by the complexity of anything, because we are all thinking sentient people. We are in a safe space where we can think without judgment. And I want you to ask me questions if you feel something is bothering you. Okay? Feel free to do that. Please do not hesitate. Any questions so far? Alright, this is my first lecture in 2 years without a mask. Okay, so congratulate all of us on living. Alright, so what I'm going to do next is, because we're doing linear system analysis, and because we are looking at linear systems predominantly, we would like to understand how to classify an ordinary differential equation in all its glory. Right? So ordinary differential equations, classification. Once we do that, and I'm not sure what purpose this needs here. Once we do that, then we will start looking into mechanical systems. We will start making use of foundational mechanical elements such as springs and damping elements to model these systems. Okay? First order of business, I'm going to write an nth order ordinary differential equation on the board. So bear with me. A suffix n of t, d to the power n y of t by dt to the power n, that's the first term. The second term, the a becomes an a n minus 1, okay, suffix, d to the power n minus 1 by dt to the power n minus 1 of y of t, then a lot of dots, then a2 of t, d square y of t by dt square as the next term after the dots. And so like this up, plus a1 of t dy of t by dt plus A naught y of t, brackets start, brackets end. This thing is equal to f of t. With your permission, I'm going to get rid of this set of lines here. Okay. So first of all, in this ODE, can you tell me what is the independent variable? Anybody?
T.
Time t. Fantastic. What's the dependent variable? What's f of t called? Yes? I am getting older. My hearing is not as sharp as it was earlier. So please speak up. The input, fantastic. It's not the dependent variable, even though the input is dependent on time. The dependent variable is the variable that you are solving for, which is the output variable, which in this particular equation is y of t. Okay? So here, t. The independent variable, y of t dependent on the output variable, f of t is the input. Okay. Now this ODE contains these terms an minus 1, a1, a naught, and so on. These are called the coefficients of the ODE. Okay, so ai of t is the ith coefficient. Excuse me. The ith coefficient accompanying the ith derivative of the ODE. Okay, so a1 of t is the first coefficient of the ODE because it accompanies the first derivative. A naught is the zeroth coefficient of the ODE because it accompanies the zeroth derivative. And so on and so forth. Okay? Please notice, these tricky fellows can be functions of time. Okay, so they can be functions of time. Or they can also be constants. Yes, sir.
In lecture 1, with the example that had the input as, I think, Q of t,
Right.
you called it, I'm pretty sure you called it, or I thought you called it a dependent variable.
That is dependent on time too, but you're not solving for it. It's a function of time, certainly.
So,
But exclusively the bragging rights for something to be called as a dependent variable is something that you're going to be solving for.
I think lecture 1 notes say
I will make sure that is the case that is taken care of. Okay? But here, the dependent variable is always the variable you're solving for. It is the output variable. The input variable is something you know beforehand. It could be a constant, it could be a function of time, or it could be zero. If the input is zero, then how does the system move? If the input is zero, how does the system move? Yes?
Is the input a function of time, so time would be zero, meaning there's no change from the first state to whatever state you're looking at?
But what if I give it something right at the beginning of time? What if I take a mass, I pluck it, and let it go? Yes?
It would only give you how that input change, or not the input, how our system changes, not what it actually is. It's going to be like how it will be.
No, so I guess I should rephrase my question. hang on a minute, I'll rephrase my question. I can take a mass, I can make it move by applying a force on it, right? Which could be a sinusoidal function of time or something that's really complicated. What if I'm not applying a force on the mass, but I'm applying something else to make it move? And what is that something else called? Yes, sir.
It's the position, so like the first state of the function.
What's that called? What's that called? The first thing that you apply at the beginning of time? Initial conditions, right? So there are two ways in which you can make a system move. One is by applying an input force, which could be there for all time. The other is by using initial conditions. We're going to spend a lot of time on initial conditions, which will lead us to the definition of state variable. Okay, so keep that in mind. So this is the basic definition of this particular ODE. I want to characterize a couple of other things. This is an nth order ODE. I'm going to write that maybe in the new panel there. Push this up. All right. This is an nth order ODE. ODE capital. The order of the ODE is the highest derivative that appears in the ODE. Okay? So this is the highest derivative that appears in the ODE. Then you have what is called as the degree of the ODE. Okay, this is the power of the highest derivative. Okay, so degree of the ODE is the power of the highest derivative. Can somebody tell me what is the degree of the nth order ODE that I have just written? 1, right? Because what is the power on the first or the highest derivative here? It is to the power 1. Okay? And then we have further classification of ODEs based on certain things. I'm going to write them down here. And I'll look at an example or two. Homogeneous versus non-homogeneous. I'm going to verbally define it. My notes will have a more detailed explanation of this. Homogeneous ODEs do not have any input terms in the ODE. Okay, so for example, if f of t in that ODE were 0, this would be called as a homogeneous ODE. I'm going to look at an example or two. Okay? If there is f of t, then this is non-homogeneous, so you have to look at a particular solution as well as a general solution for this. Alright? Then I have linear versus non-linear ODE. We will exclusively study only linear ODEs, and in the instance that we end up with a non-linear ODE, we will employ the process of linearization, making use of a Taylor series expansion. I'm pretty sure you've come across Taylor series, but we will go through the details again. Okay? What's a linear ODE? A linear ODE, verbally, a linear ODE is linear in the dependent variable and all its derivatives. Once again, an example begs to be discussed here, which I'm going to do so. Okay? The last classification is constant coefficient. Coefficient versus variable coefficient ODE. What do you think this is going to be? If in the nth order ODE, if my A1, A2, A3, A4, all of these fellows, if they're constants, that's a constant coefficient ODE. Even if a single one of them, if they become functions of time, I do not have a constant coefficient ODE. I have a variable coefficient ODE. The solution techniques are vastly different, much more complicated. Okay? So I'm now going to take an example, walk you through all of these things. Right? So let's do that. Before I break these things, I need to bring this. This is my good workout for the day. All right, let's take an example. All right, here is the example. I'm just going to cook up something, okay? So, z triple dot of t whole square plus say this is minus. So here is the example that I've written. Please notice z triple dot of t whole square e to the power minus 2t times z dot of t minus 2 sine t is equal to 0. What does the dot represent? The dot represents differentiation with respect to time. Fantastic. So from now on, I'm not going to write dz by dt, d cube z by dt, and so on. It is going to be z dot, z double dot, or y dot, y double dot, x dot, x double dot. The dot represents differentiation with respect to time. So one dot is defined as d etc. Okay? All right. Let's get cracking. First things first, you always have to write ODEs in their proper standard form. What is the standard form of an ODE? Okay, so here is the standard form. The right hand side of the ODE should contain the dependent variable and all its derivatives. Dependent DEP dot dependent variable and its derivatives. This is equal to the rest of the stuff in the ODE. Okay, so you always write every ODE in its standard form. The left hand side of the ODE, which is on my left if I am facing the board, is going to contain the dependent variable and all its derivatives, and everything else, throw it onto the right hand side. So my first question to all of you here is, take a look at this guy. Is it in the standard form? It's not in the standard form because of this pesky 2 sine t. Take the creature, put it onto the right hand side, then we are in business. So let's do that. So I'm going to have z triple dot of t whole square plus e to the power minus 2t z dot of t. This is equal to 2 sine t. I cannot emphasize this enough number of times. I do not like to see things like this. I want everything in the standard form when you submit your assignments, because it makes sense. And there is a reason for why we are doing this, because the right hand side contains all the output variable and its derivatives. The left hand side is the cost, which is the input for the system. Okay? So that being said, what is the order of this ODE? It is the highest derivative that appears in the ODE, and this is going to be 3. Okay, so order is 3. Let's make it a little fun. Hang on. Let's say I have z dot to the power 4. Why not? Right? Now tell me, what is the degree of this ODE? It is 2. Don't be fooled by that 4 creature. That 4 is not on the highest derivative term. The degree of the ODE is always the square or the power of the highest derivative, so the degree is 2. Is it linear or non-linear? Yes, question.
Can you go over why exactly it's 2 again?
Oh yes. So you look at the power of the highest derivative term. That's 2. Even though this term has a power 4. But that's not the highest derivative, you see. So the degree is always the power of the highest derivative term. Okay?
I have a question.
Yes.
I remember my math professors used to have us, like, if there was a 3 in front of the third derivative, for example, she would have us, like, divide everything by 3.
Divide everything by 3 in front of here?
Yeah, like, let's say that there was a 3 there.
Okay.
She would say for standard, you would have to divide everything by 3.
Not necessary.
No.
Not necessary, because that is math and this is engineering. That's the short answer. That's the short answer, but hang on to your horses, because what you will see is mechanical systems. You're going to have this foundational equation which is going to be in your nightmares all through. mx double dot plus cx dot plus kx is equal to f of t, where the mass is the m term, the stiffness of the spring is k, and the damping constant is c. And then we will go back to your math teacher and tell them that they're right. We will divide through by the mass, or we will divide through by the stiffness. Depends on what we want. Okay? So there is nothing hard and fast about having a term. All right, my next question. Linear or non-linear? The dead giveaways here are these squares and these to the power 4. Right? So I look at the dependent variable. They are not linear anymore. Its derivatives are not linear anymore. So this is a non-linear ODE. Non-linear because of these two things. Okay? Homogeneous or non-homogeneous? It's non-homogeneous because the right hand side has the 2 times sine t. Okay, so it is non-homogeneous. Constant coefficient or variable coefficient? Look at the coefficients accompanying the dependent variable and its derivatives. I don't have a time varying quantity here, it's 1 times z triple dot square, but the next coefficient is e to the power minus 2t, so this tells me that this is a variable coefficient only. Okay, so this guy here tells me this is a okay. One more example, and then we will call it quits on this. And I'm happy to answer questions as I keep sliding the board up and down. Okay, it's going to be a challenge. Yes, yes, go for it.
So 2 sine t makes it non-homogeneous because of what exactly?
Because that's a term that's non-zero on the right-hand side. A non-homogeneous ODE requires a particular solution to that ODE for that particular forcing term. And so that's why it's called non-homogeneous. If that side were equal to 0, then I would just have only a general solution for that ODE. Okay?
So if it's anything that's not just, even if it's a constant,
Absolutely, it could be just 2. That's also non-homogeneous. Absolutely, absolutely. Yes, yes.
I have a question about the coefficient. So if you have like 4 constants and then 1 variable, it makes the whole ODE variable.
Cooks the whole goose. Okay? Even if there is 1 coefficient, that's a function of time, end of the story. Okay? So here is another example. X double dot, okay, plus 3x dot plus 4x is equal to 0. First question, is it in its standard form?
yes.
Yes. Why? Because the left-hand side contains the dependent variable and all its derivatives. What is the dependent variable? X of t. Right-hand side contains 0 because there is no applied force or there is no applied cause on this problem other than initial conditions, which we will discuss as time goes on. Okay? So first of all, this is in a standard form, and then we start writing the order of the ODE. The order of the ODE is the highest derivative that occurs in the ODE, and in this case, this is going to be a second order ODE. What's the degree? Degree is 1. It is the power of the highest derivative. Is it homogeneous or non-homogeneous? It is homogeneous because the right hand side is 0. Yes, sir.
So, I know at the top you have 2 sine t, right? And then on the bottom you have 4x. So, I guess I'm wondering, what is the difference between, is the x not included in the dependent variable and derivatives? Or
In this equation, x of t is the dependent variable.
okay.
X of t and its derivatives, x dot, x double dot, and so on. Those are the dependent variables. Time is always the independent variable for us. And if I say something is a constant, then that's also a function of time, it just doesn't vary with time. That's an oxymoron, of course, right? But if it's a constant, that's also a function of time. It's just constant with time. Okay? So this is still the dependent variable here. This is not going to be going to the right hand side, and it is still a homogeneous ODE. Right? Constant or variable coefficients. Look at each and every one of them, and as one of you pointed out, if I had written this as 4t times x, that would be a variable coefficient ODE. That is not the case here. I'm erasing that and writing it as just 4x. So this is a constant coefficient ODE. Yes, hang on, right? All right, go for it.
So even though the coefficient of the second derivative is x.
That's not a coefficient.
Okay.
Right, that's not a coefficient. A coefficient can be a constant or a function of time. Not an implicit function of time, an explicit function of time. You see, that x there is a dependent variable and that was wantonly put there for a purpose. Fantastic question. What was the question? What about this guy? Isn't that creature also a function of time? Of course, right. It's a function of time. But it's a dependent variable, for heaven's sake. And so that is not going to act as the coefficient, because if you look at the coefficient, it is an explicit function of time, or in the worst case, it's a constant. Okay? So what does this x of t play a role here as? It actually makes this equation non-linear. Because if I now look at the dependent variable, it's multiplied by its derivative, so this term is no longer a linear term. It is a non-linear term, and so this makes it a very scary differential equation. It's a non-linear ODE. I do not know how to solve this damn thing. Okay? This is non-linear. Of course, we know how to solve this using numerical methods. The Runge-Kutta techniques and so on, ODE 45, etc. Okay? Which we will be seeing as well. Yes, question?
Why is it non-linear again?
It is non-linear because you see that there is a product of the dependent variable and its derivatives. So that's no longer a linear type. It's a mixed type. Okay? So if I have a product of the dependent variable and its derivatives, or if I have a square or a cube, or to the power of the dependent variable, those are all non-linear ODEs. My notes has a few more examples of this type. Okay, and please go over it, and you'll be in a position to answer the first homework. Last thoughts on these examples. Good questions, keep them coming. I love it. Yes, sir.
Are all the classifications that you use, they're always based on the dependent variable? You'll never look at the independent variable and get the power there.
Absolutely, absolutely. So, the great news is that we have only one independent variable. Otherwise, we will be looking at the classification of a partial differential equation, which would be a hyperbolic, elliptic, or a parabolic partial differential equation. So that will depend upon the nature of the relationships and so on. Okay? Two questions. First question.
Can you explain one more time why it's constant?
Oh, constant coefficient. Because you see, each of these coefficients that accompany the dependent variable are constants.
Why doesn't the x get included though?
That's a dependent variable.
Okay.
That's not an explicit function of time. It's implied that it's an implicit function. If it's a coefficient, I don't have the nth order ODE, but if it's a coefficient, they are going to be explicit functions of time. For example, 2e to the power minus t. Or they will be constants. Okay? One more person.
I was going to say, sometimes like there are equations where you can simplify them and it turns out that it's actually linear on the same denominator. Will we have like if that 3x dot wasn't there?
If that 3x dot was not there, that would become a linear ODE because you can divide through by x. Right. I will try to make sure that we don't encounter such beasts, but maybe because you reminded me of it, I will make sure that you do encounter it. Thank you for those ideas. These are all exam questions. All right. I'm going to move on now. Write out two more things and then go to the study of mechanical systems. Okay? All right. Time-invariant systems. So linear, because we are doing linear systems for the most part, I will just quantify it as linear. Linear time-varying systems and time-invariant systems. Time Is my writing still good for people in the back? All right, fantastic, fantastic. Please let me know, okay? This is the definition. And I'll tell you a really easy way to figure out if ODEs are linear time varying or time invariant. Okay, so the definition is the following. So say we have a linear system. Let's say that we have a linear system. Let's say that the input to the system is f of t. Which in turn produces an output x of t. Okay, so let's say that this is the system that I have. Beautiful system. Great system. This system is called time invariant if for an input f of t minus tau